Welcome to the second session of the Maple Conference. This one's entitled Gems You May Have Missed. I hope you're enjoying the sessions, the conference so far. In this session, I'm going to talk about new features in Maple 2024. This isn't the conventional what's new promotional talk. I'm going to skip many of the big features that you've probably already seen and focus on some of the features that you may have missed. For example, I'm not going to talk about AI. We're going to get to a lot of that already this conference. A talk with this same title has been done many times throughout this year so far, and by at least 4 other people at Maplesoft. And I was given their scripts as a foundation for building this, and I felt that I had to go through and pick out the features that I liked or were closest to me. And it's amazing how each of the other presenters had different lists and picked out different things. That's the great thing about Maple and mathematics in general. There's a wide, deep pool area of lots of areas of interest, and there's usually something for everyone. So in no particular order, of the thousands of changes that went into Maple 2024, let's see what I picked. So the first thing, over the years, I don't know how many times I've examined an expression, and with the fist in the air, I've said, why can't Maple do this? Then as I'm conversing with somebody in the math group, usually, or an expert, they would calmly explain, because the result that I was looking for is actually not correct. Maple isn't giving you that result because you're asking for something that's wrong. So here are a few things in Maple that we used to do for convenience or as it was expected or it was symbolic. So things like, is w squared equal to the absolute value of w squared? That's actually not correct in all domains. If we add the assumption that it's real, then we get the answer we're looking for if we were expecting a real domain. Same thing with w equal to the conjugate of w. And this last one, I had to look at for a while because it isn't intuitive. But if you look at some of these counterexamples, you'll see why these aren't true across the board. So Maple, in Maple 2024, we've tuned some of these answers. We've improved the is and the could it be commands. And these are kind of foundational things that operate behind the scenes in simplify, in solve, in a lot of different areas of Maple. And it's important to have the foundations right. And if you're looking for domain-specific answers, the assuming facility is fantastic for zoning in on a specific area that you're looking for. So in the same vein, we have an example like this. In the past, Simplify, for internal reasons, has tried to stay with sine and cos. So now we've expanded that. So that might be something that internally is easier to work with because you have only a fewer number of special functions to work with, but it's probably not what the user is expecting. So now we look at, Simplify looks at all the trig functions and hyperbolic trig functions and tries to find the simplest result in any of those. And this answer involving a cotangent is a lot simpler than leaving it alone as in terms of sine and cos. Another trig example, we can look at a shifted sine cos here. So we can see that this is just our cos, and we can get rid of this extra pi over 2 term. So due to improvements like this, and there's a whole bunch of others, I've just selected a couple of them out. We can, for example, solve this integral now. right? So we do something foundational and simplify and is and could it be, and now we can do more integrals. So actually, for anybody wondering about this expression, I promise you that it's sine of arccos of x that is exactly x. But while I'm here, I might as well look at this expression because it is an interesting plot. So let me just put that on the screen. And that's actually one really nice thing about Maple that I love is whenever I see something and it scratches my head, I usually plot it to see what I'm really looking at. And this is going to lead to the next feature I want to talk about. We've had in Maple for a long time some drawing tools. So if you go over to the top here and click on drawing, now I have a bunch of controls that let me draw over top of the plot. A new one this year is an arc tool. So I can put an arc on here. Actually, I'm going to delete that. I can add an arrow to it. And let's choose this arrowhead. And now I need to click on the arc tool again. I'm going to put that on the over top of the plot, maybe adjust it a little bit. And now I'm going to go back to my drawing, and add some text. So I can type in pi, hit escape to get command completion, and I'm just going to choose the pi symbol. I can do natural math notation and type in here. So that's just a little thing, but it's a reminder of one of the nice tools in Maple that you can annotate over top of plots, and now you have this ability to have curved lines. So now let's look at some 4-dimensional plots. So we have a new coordinate color scheme option. So a coordinate color scheme lets you define a plot and color it. So that's the 4th dimension is color, using a custom function. So here I'm going to do Z coloring, and my custom function is to compute the color based on the distance from the Z axis. And the new thing is that I can choose a palette. So here I'm going to apply the cool warm palette. So based on how far away from the Z axis, we're going to map in that cool warm palette. So closer to the Z axis, you're going to get the cool colors, the blues. Sort of medium away, you're going to get the whites, and the furthest away, you're going to get the reds. So similarly, we could do X, Y, Z coloring. So now I'm going to base the coloring on all 3 coordinates, and I'm going to center it not at the origin, but at 2 pi, and 0. So I'm going to add the same cool warm palette, but now instead the cool part is at that point that I've selected. So I'm using a distance metric, and then the further away from that point I get, it's going to have a gradient towards the warm colors. So I can immediately see where I am in that plot and in my data. Just one more, I'm going to cut out the Z here. That gives a little bit of a different look to it. But it's really powerful for visualizing. And complete the example, I'm going to choose a different color palette, color scheme. That one's a little bit darker. I could emphasize something different in the plot. Here are 6 of the different color palettes that are built in. There's a bunch more. And if you look at the color tools help pages, you can find a number of them. And these are specifically designed to have a gradient that maximizes the contrast, or in some cases, minimizes it. So now here's a simple command, but I really like this one. So we have a new pyramid geometry in the plot tools package. So along with all the other geometries, we can now add a pyramid. So the default is to have a square base. And here we've got one that's 1 unit high and looks like 1.6 units wide at the base. So let me change that so that I have a square base still, but I'm going to have it 2 units wide, and I'm going to change the height to be 2 units wide. So I can configure the properties of a square base triangle, or I can introduce a different shape as the base of the triangle and of the pyramid. So here we have a hexagon as the base. And if we want to get really fancy, let's show you what a heptagram looks like. And I'm going to use that as the base of my pyramid. And so it looks, there's the heptagram as the base, and it joins at a point, so therefore it is a pyramid. If you want to Google paper star pyramids, there's a fascinating rabbit hole you could spend hours down. So here's a rather substantial new package in Maple 2024, the hypergraphs and matroids package. Now, this is nothing like my area of expertise. Hypergraph is slightly different than a graph. It has hyperedges and vertices. And there was, in one of the examples, a hint at it, at putting together a hypergraph that's based on recipes and food ingredients. So let me try explaining how this works. So I've put together a few recipes. So a poutine has potatoes and cheese, a stew has potatoes, carrots, and beef and onions. And I've created a hypergraph of these ingredients and these recipes. So now I have, you can see the graph. There's a node here that you can see connected the lettuce, the carrots, and the onions. And that is the salad recipe. For example, here, beef is connected to carrot and onion, and that's, let's see, that's another one of the recipes. Yeah, oh, and the potatoes. So that's the stew. So this node connects 4 ingredients. So we can draw that, and then we can compute with these hypergraphs, for example. So I'm going to compute the minimum. And so the min of food hypergraph are those recipes which require a minimal set of ingredients. In other words, removing any ingredient prevents any recipe from being made. And so this is the vertices and edges of this new minimal graph, and that's the visualization. And the max here I've computed are recipes which maximally use ingredients. So you cannot include an additional ingredient to make a bigger recipe. And here is the list of ingredients and the pairings. And that's what this graph looks like. And then you can do other computations like a traversal. In this case, a traversal are all the sets of ingredients. You could conceive that an adversary could steal from your fridge, which would prevent you from making any recipe. So you can see if somebody stole a carrot and a potato based on the landscape of recipes, you wouldn't have enough ingredients to make any of the recipes. So obviously this is sort of a trivial example and I stumbled through it. There's much more power in the real application of this. So let's look at regular graphs. So in the graph theory, we have a new relational graph command. And so for this example, I'm going to create a graph with 16 nodes, and all the edges will connect those nodes based on this mapping. So I'm using the number theory R co-prime. So we're going to get an edge if the two numbers are co-prime. So this is called a relational graph. So look at a number like 5, and you can see that it's connected to all the other nodes, except that it's not connected to 10 and it's not connected to 15. And we can verify with this with the neighborhood command, and you can see you get a list of all the connected vertices that are connected to 5, and it is missing itself, 10 and 15, which matches the coprime requirement. Sticking with graph theory for a minute, we've added a whole bunch of new special graphs, a lot of the Archimedean solids, and I'll just scroll through these. So you have the planar view here and the 3D view here. And these would be very cool if you could make soccer balls that look like this. So there are a number of these added in Maple 2024. And we've also added a Mobius ladder graph and a Wagner graph. I think these are really fun to look at and to experiment with. So I'm going to introduce a language change. This is a really nice, convenient function. So here, let's define a bunch of lists. And we have element-wise operators in Maple. So for example, I can use the plus tilde operator. So the tilde following any infix operator will cause the operation to be applied in an element-wise fashion. So I've got A plus tilde B, so that means that it's going to add up each element of the container. So it's going to get 5 plus 3, 9 plus 4. I can change that to say minus tilde, and then we have element-wise subtraction. Now Maple is sort of unlike any other language. You can also do this for any function name. So if I have f a tilde, that's going to apply f to all the elements of the container that you're passing in. So what's new is if I wanted to do, say, exponent, I have to, in 2D, I have to put in \caret, and that gets me the element-wise exponent. It's not very nice. Similarly, if I wanted to do division, I'd have to do \divide, and I'd get my element-wise division. And there are other sort of 2D constructs like square root that I would have to type out in command form in order to get the element-wise application, or use a function like map or something like that. So, but what about if I wanted to do this all together in a nice big 2D expression where I wanted the times, the exponent, the divide, and the square root all to be applied element-wise? If I try this here, it's going to give an error because it's trying to do operations on all the lists. But there's a new command in Maple. We can wrap this whole expression in the element-wise command. Put my cursor here. And now I get all of these operators converted to the tilde form, the element-wise form, without affecting the look of it. So I get the element-wise application. So I think that's actually a really nice new feature. Okay, so eval HF rather. So in Maple, we have, Maple's a large language. It deals with symbolics. It deals with infinite precision numerics. It deals with infinite precision integers. And these are all very powerful. Sometimes we want to strip out a lot of that functionality and deal with just hardware floating point algorithms. So the eval-HF subsystem of Maple lets you evaluate a procedure numerically using hardware floating point. So there are limitations to this subsystem. One big one is that you can't pass symbols around, but we have removed one of the limitations in the latest version of Maple, and that is we now support the try-catch clause. So if we look at this procedure, we're gonna pass in 0 as the second argument. So instead of doing a division by 0, this procedure checks if the denominator is 0 and then raises an error, but it immediately catches it and uses a default value. So I can call this inside of eval-HF now, and the try-catch works. In previous versions, it would say, I can't do anything with this procedure because there's an unknown try statement that I can't handle. So this lets you do more procedures in that numerical subdomain. Signal processing. Signal processing is one of the core engineering packages that comes built into Maple. And every release, we try and add some more algorithms. In this release, we've added a few. One of them that I'd like to highlight is the response spectrum plot. So here we're gonna import some data. So this is frequency data, vibration data from an earthquake. And we can analyze this. So compute the response spectrum using various parameters, and then plot this. And this is something requested and used by engineers that need to do signal analysis. Sticking with engineering for a second, units is very foundational within Maple and Mapleflow. I think that Maple contains the largest collection of known units compared to any other software package. And so we want to keep expanding all of the algorithms to know about units, and we want to make it more and more efficient. So there's one really significant change that may not sound significant on the surface, but is sort of fundamental. So I'm going to start here by loading the unit package. I'm going to have a matrix that has quantities in meters. I'm going to have another matrix that has quantities in seconds. And I'm going to compute the product of first one times the inverse of the second. The real key here is that these are all data type float 8. So that's hardware precision floating point number. And the inverse and the multiply is done using standard numerical recipes and parallel using very, very fast algorithms. And if these were 100 by 100 or bigger matrices, it would be instant. Whereas in previous versions of Maple, it would go down the symbolic route because you had to pair the unit and the number in one entry of the matrix. Now we have split those two quantities so that you can create a float8 data and associate a unit with it. And internally, it keeps those separate so that it can pass the data to the fast algorithm and pre and post process the units. So that's actually a really important change. Additionally, we've added lots of hooks into the statistics package so that it can look at inputs and outputs and see that there's unit quantities and make sure that the result quantities match the unit inputs. So a number of commands in the statistics package now support units. So rounding out the baker's dozen, I'm just going to quickly mention steps. So Laurent hinted at these in his keynote. We have, I think, about 20 different algorithm domains that we can give steps on. So we've added partial fraction steps, and we've beefed up all of the other steps algorithms to support harder and harder inputs. So, for example, in solve steps now, we have better support for logarithms and exponentials, and these are actually really significant. It goes through all of the logic of getting an answer and checking domain requirements and excluding answers that don't meet the domain requirements and formulating the final answer in the solution. So here's another example using log. Here's an example that is a relation with absolute values. And this even plots the domains and gives the test points that it's looking at. So there's a lot that has gone into, so we haven't added a new command, but we've really beefed up some of the existing commands behind the scenes there. The other aspect, the flip side of steps, is the check my work. So rather than the student asking for steps, the student supplies all the steps and then can ask whether those are the correct steps. So for example, here we're doing a factor practice. So it generates this box with a check my work button, and the student can enter the various steps towards factorization and then click the check my work, and it will tell them how they've done. There's also simplify and other check my work algorithms. I just paused there to grab one of the inputs, because this is one of the real powers here, is that I can just simply add output equals link and execute that. And now I get a hyperlink to a web page. And if I click that, it takes me directly to Maple Learn. And I have a factor practice where I can enter some bogus steps and try check my work. And of course, it highlights these two steps as being unrecognized. There's also a try another button now in Learn, where it will give me a new factor problem. It will analyze the existing one and try and come up with one that here is factorable and is the same degree as the starting problem. All right, I think I'm just about out of time. Maybe I have time for one or two questions. I haven't been watching the chat. Are there any questions in the chat?
There are a few questions. Let's see. There was somebody asking about support for units in ODEs. I think we have talked about that. Well, I'll let you answer that question.
I was going to say the same thing there, Eric. Eric, you know better than I, as the head of the Mac group.
Yeah, we've talked about this and thought about it. We haven't implemented it yet, but it's you know, at some point on our priority list. Haven't gotten around to implementing it yet.
Right. Okay, one more question.
So another question is a question about whether the new editions include the crystal classes. I think that references the different types of crystal lattices that there exist. Again, I think the answer is we don't have that implemented yet, although I might be wrong there.
Yeah, I would have to look too. there were a lot of graphs already built in prior to the ones we added, so it would be good to look and see what else is there. I'm sure there are some crystals, maybe not all of them. All right, well, thank you. And I guess we'll proceed to the next session.